Hi, everyone, and welcome to our next short talk today by Zurich Instruments. This is really exciting. We have two speakers. I know that we are a little bit late on schedule, but the talks are fantastic, and we want to listen to all of them. So let me introduce them. Vikrant Mahajan is engineer by training. He joined Zurich Instruments as VP of Sales and Operations USA in 2020, and leads the US subsidiary based in Boston. Prior to joining Zurich Instruments, Vikrant managed LED retrofit and smart home, lighting business segments at Ostrom, Sylvania, and Ledvans. Vikrant began his professional journey in 2005 at LabSphere Inc. as an applications engineer manager. At LabSphere, he also managed calibration lab and multiple product portfolios. Very interesting career. And we also have Tobias Thiele. Tobias Thiele is an application scientist and product manager for quantum technologies at Zurich Instruments. His background lies on the intersection between solid-state system, atomic physics, and sensitive magnetometry applications. In the US and Europe, he has worked on hybrid systems for coupling Rydberg atoms to superconducting circuits or atoms to nanophotonic crystal waveguides, trapped single atoms in arrays, and developed a sensitive absolute atomic magnetometer. Very interesting. Okay. Looking forward to your talk. Vikrant, whenever you're ready, you can start sharing your screen.
Absolutely. I hope you can see my screen now.
Yep.
Okay, great. So good morning, good afternoon, good evening. Thank you all for joining our talk presentation here. As my name is Vikrant Mahajan, and I'm going to be presenting with Tobias, my colleague. Let me start with who we are at Zurich Instrument. Our headquarters is based in Zurich, Switzerland. We are over 100 people, more than 100 people now, and we are a global company in terms of our outreach. We have offices here based in the US, in China, and other countries, as you could see. What's interesting to note is we are founder-led company. We are run by scientists for the scientists. So we are all very passionate about science and technology here at Zurich Instruments. So briefly talking about our Zurich Instrument USA team, we are a newer team, but growing very fast here. We're based here in Boston, Massachusetts, so close to Boston. And the team here in the US is a very diverse team with really application scientists, with technical sales, with marketing, and majority of our team here in the US is PhD physicists. So again, speaks the same way, as I said, passion for science. Now, our US team is involved in a lot of quantum projects as well as quantum institutions and organizations. We are actively working on projects funded by DARPA, DOE, IARPA, and we are part of a lot of reputed quantum organizations here in the US, like Chicago Quantum Exchange, Qubit, QSA, and so on and so forth. And when Tobias, in his talk, is actually going to talk about more about our quantum programs and our quantum initiatives. So I'll leave that part for Tobias. So you could see there are many open positions that we have at Zurich Instrument. I'm going to request you to please go on our website and visit our career page. The link is provided here. Please visit our booth and you'll find more information. Please talk to us. But the position that we are featuring, and I'm going to be talking at length here, is really the position based here in our Boston office, is the application scientist quantum technology. It's a very dynamic role, dynamic in the sense that it provides an opportunity to be at the forefront of the quantum technology and support some of the cutting edge research, being part of this quantum community. As I said, it provides a lot of global experience, so a lot of exposure in terms of an international diverse team. And I think what's most interesting is applying the knowledge, the quantum knowledge, to solving some of the most complex problems working with some of our customers. So please visit our booth, and Tobias Ed, they are our application scientists, and they're very happy to speak to you and kind of walk you through how a day for application scientists at Zurich Instrument looks. So please come and talk to us and firsthand get an exposure to the day-to-day activities. Now, last slide from my side is why join Zurich Instruments. I think this is really looking back and looking at my own experiences. Some of these points really resonate with my experience here at Zurich Instrument as well, and most of my colleagues. I think some of the important things is we stay close to research. We stay close to research, either in terms of academic research or industrial research, by really staying in forefront of science and technology. We are a growing company, so there are a lot of opportunities for personal growth, for career growth. It's a great team of very dynamic, diverse, international colleagues. So a great working environment in that sense, with great team spirit. We value leadership. We value people taking lead and initiative and bringing in change in a positive manner. So I think that's a very good work culture that we provide. And I think I would say our biggest asset is our great customers, very wonderful customers, and some of the best quantum researchers around the globe. So an opportunity to connect and work with those wonderful customers, I think that's another thing. So that being said, I think I'll pass it along to my colleague Tobias, who's going to talk about quantum program and more quantum initiatives. So on to you, Tobias.
Okay, so thanks for this, Vikrant. I think I'll need to now share my screen. One moment.
Absolutely.
Good. Good. So now, thanks again. So I will tell you, as Vikrant said, I'll tell you now a bit more about what we at Zurich Instruments now do in quantum technology. And so what is our ambition? Well, we want to help build a scalable and fault-tolerant and, of course, useful quantum computer. So how can this be achieved? Well, one of the key assets here is really that we need to be up to date and sort of fully on top of the progress of the field. And only if we can really predict where the field actually will be going in the next few years, we can be successful. And for this, we as Vikrant said, we work really closely together with people at the forefront of development, both in research but also in industry. And essentially by talking to them, we then get the right inputs to develop exactly what is needed, which is in our case, classical and application-specific qubit control hardware and software. And currently, our systems are focusing on superconducting and semiconductor qubits, but we also, of course, have great solutions already developed for atomic and color center systems, for which we're sort of continuously increasing our fit. So why are we talking to you today, and why is this interesting? What are the people that we're really looking for to achieve this goal? And this is really strongly determined by what we do and how we approach the market and our field and our research. And what you can see here is sort of this quantum stack, which you probably have seen before, which essentially describes all the different components which are needed to work together to form a scalable quantum computer. And at the bottom, you have sort of the quantum layer or the quantum system with the qubits and the qubit chip. And then if you go higher in the stack, then first comes the classical control electronics, and then sort of different levels of software abstraction, until then in the end, at the very top, you're able to just essentially write the bare quantum algorithm, for example, like a Shor or a Grover algorithm, and where you're agnostic to which qubit type is actually running the calculation. And we sit at the center, and you essentially could call us sort of the turning gear, because we're making the control hardware, which connects essentially on the one hand to the classical work, but also to the quantum world. This means that we really need to closely understand, of course, all the requirements in the field and the technology of the quantum device itself. But of course, we also have to connect and talk and approach to these higher levels of the stack, which want to actually talk to the control electronics and ultimately to the quantum computer. So what we're really looking for is really this team of very broad expertise, and this is what we are already today, which makes actually working there exciting, from with expertise sort of in software, firmware, and hardware designers, and of course a lot of quantum scientists, which are constantly working on sort of developing our offerings. And often these expertises also overlap, so you can easily have people with a degree in quantum physics or other fields worked on an FPGA solution or some software solutions if they want to and if they're interested in that. So, but essentially, just to develop the instruments was, of course, not enough. And what we really need is sort of this market experience, as I said, and the know-how. And essentially, about half of our company is really working in this marketing department. And these are often the application scientists, but also technical sales, which really then understand the application, the field, and really closely work together with the researchers, essentially almost as part of their team. And the learnings and take-home messages then from these interactions, they then provide the input which are needed to develop and configure the right thing. And this is also why essentially all our product managers are application scientists, so coming from the marketing department. And from this interaction, this is, so, for example, how we also came up with these two thrusts, which we typically promote, where our instruments cater. And so you have on the horizontal axis, you have the so-called technology thrust, which is where the field is trying to build better and better building blocks for a quantum computer. This can be coherence times, gate fidelities, and speed, and fast initialization of the qubits. And on the other hand, you have sort of the scaling thrust, where you try to see every year scale up, and where you really try to think about, okay, what is really needed to scale up your system size. And what you see here is a few of the customer sizes or instruments and systems that we are currently working together with customers to set up and control. And what we do is our control electronics really supports both of these thrusts. But the problem is that these different thrusts, in the end, of course, have different requirements, and they sort of need different attention to create sort of the highest value for our collaborators. And these collaborations between us and the teams then here are really important, because especially if you want them to people in the end to be able to use the same tools, the same systems that we develop, such that they can go sort of back and forth between different tasks in the different thrusts without the complexity of maintaining two vastly different control approaches. And these thrusts are sort of therefore also reflected in the generations of our products. And we are actually in the field already since roughly 7 years by now. And we started out at that point with some generic instruments, AWGs and quantum analyzers, which read out the qubits. And then essentially we continue to develop our first generation quantum computing control system, which already at that point, a few years ago, could scale to about 50 qubits. But it's still today a very flexible solution, and it's sort of mostly suitable for the technology thrust. Now, with our actually recently launched second generation, we are now supporting even larger qubit numbers. Nowadays, it's more than 100 or even 200, depending on what the requirements of your actual qubits are. And we're still developing this platform further. And in fact, it actually doesn't stop there. And because even today, we know how to develop a system for 1,000 qubits. So if the time comes, we are ready. And just to show you or give you an example why we are so excited about this new generation, it really sort of takes the system integration onto sort of the next level. For example, both of these instruments, which you see here, they are designed to either read out or control the qubits, and they essentially consist of several channels. Okay, and each channel, which is essentially defined by two of these air slits, or which you can find between two of these air slits, integrates either a full control or a full readout setup. Okay, so everything which you actually need to set up your full classical control system is a computer, a set of microwave cables which connect from these instruments directly to a cryostat. And so because of our involvement in the field since 2014, we actually came a long way, and our customers have achieved already some major milestones and generated many success stories. And here are a few of the places that Vikrant mentioned, which are in the US, but we also have a few more which are worldwide interacting with, which we are currently strongly collaborating. So for example, there's ETH in Berkeley, more on the academic side, focusing on superconducting qubits. We have Quantum Inspire, a government-funded project which works with spin and superconducting qubits at the same time, and where you can actually log on and have our instruments running 24 hours. Then there's IQM, which is a startup selling quantum computers to researchers. And of course, we support Intel with their spin qubit research. So in total, this is already a good variety of example projects that we're interacting in. But in the end, our customers also produce outputs now almost at the day level now by using our instruments. And on the right, what you see here are some of the recent success stories in form of publications. And this, of course, each publication gives us a lot of pleasure and motivation to really push the edge of what is doable nowadays. And a few notable examples here are the first implementation of a Surface 7 code, of course, the impressive performance on these very short gate operations by IBM, or feedback operations where you stabilize quantum states over a significant time, longer than the coherence time of the individual qubits. So with these nice examples from the field, maybe let's end this presentation here. And if you want to find out more about what exactly we do and how work is, especially as an application scientist, come meet Ed and me at our booth. I'm, for example, working here in our Zurich offices, and Ed is working in our US offices and supporting the quantum market from there. And with this, I'll end with our punchline, which is your qubits controlled. But if you want to control also your career, then again, let's just contact us either directly via the website, come to our booth, or even just write me a personal email, given my email there. So thanks a lot.
Thank you very much, Tobias and Vikrant. I really like that. Control your career. You cannot control it, right? Well, at least we can control qubits, apparently. Great. So we are running super late, as you know, but let's just try to answer at least one of the questions. I'm going to start with the first one from Alexandra Pinto. She asked, which branch office has a smoother application setup for sponsoring working visas? That's a very good question.
So I could try to address that. I think the working visa becomes very specific depending on what country the role is based in. So, for example, the requirements here in the US are different than in Zurich or other offices. So my recommendation is please come and talk to us. We also have our HR specialist at the booth, so we could certainly address those questions more specifically.
Perfect. So let's just finish here. Thanks again, both of you. And please just go and visit the Zurich Instruments booth. I think that you can learn a lot about what they are doing and ask all your questions. I will pass the questions that have been asked, just if you want to answer in later on. So thanks again and have a good day and see you soon. Bye.
Thank you.
Perfect. Thanks a lot.
Bye.
Good night, everyone.